In this tutorial, we'll cover the transformation of stress and strain.
This chapter is about finding the maximum normal and shearing stress on an object that is under a combination of loads that includes torsion, axial, bending, and shear. We will first take a look at this curved beam to illustrate the main steps in solving problems related to this chapter. On this beam itself, there are two forces, P1 and P2. We are asked to find out what is the maximum stress on this beam. And through observations, this occurs at the bottom over here, and hence we cut it. So this is the small section from the bottom of the beam. The stresses on different sides of the beam itself are different, and hence we consider elements A and elements B. To find maximum stresses on the cut, there are several steps. We'll go through them step by step. We'll first visualize how the external loads itself will result in different kinds of internal loads on this section, and we'll do it force by force and axis by axis. First, let's take a look at P1. P1 itself is along the z-axis, and it cuts x and y-axis. As such, it will only result in a force that is in the z-axis and does nothing to x and y-axis. For P2 itself, let's take a look at what it does to the x-axis. It is at a distance away from the x-axis, and this distance is the z-axis, z distance. As such, it creates a moment about your x-axis. And this moment is P2 multiplied by the distance z. For the y-axis, P2 is in the direction of the y-axis. As such, it will cause a shear in the y-axis. For the vertical axis, which is the z-axis, it is at a distance x away from the z-axis. As such, it will cause a torsion about your z-axis. You can resolve the moments as well as the torsion using your right-hand rule. After we have found the internal forces due to external forces, we are now ready to resolve the stresses on elements A and B due to these internal forces. For element A itself, we first draw the positive convention. The positive convention for an element is tension on all sides, as well as the shear stress that's of this form, whereby the right-hand side, the shear stress is upwards. For element A, the right side itself is normal to x, as such this is sigma x. Top is normal to z, as such this is sigma z. And then tau is just tau as z. We then find the stresses axis by axis. Let's look at the x-axis. On the x-axis, we have a moment, P2x. For bending moments itself, there is tension and compression on either side. On the side of the A element, we have tension, and since A is at the edge, it has maximum tension. And we can use the equation sigma equals to my over I, where m is P to Z. For the y-axis, we have shear P2, and for shear itself, maximum shear stress is at the center. As element A is at the edge, therefore there is no shear stress. For the z-axis, we have P1 that's normal to the surface. This causes normal stress, and itself is in tension. As such, it is positive because it's in the same direction as the positive convention. Same thing for the moments we resolved earlier. It's also positive because it is undergoing tension for A in the z direction, which is the same as the arrow here. If instead this itself is downwards, P1 is downwards, which causes compression, then the sign here will be negative instead because it is opposite to the arrows. On the z-axis, we also have a torsion, P2x. P2x itself, using right-hand rule, it will cause the top side of the surface to go to the right, which is the same as the positive convention. As such, this is a positive sign, Tc over J. Sigma x itself is just 0. We also have element B here, which I will leave it to you to work it out. We see from elements A and B that there are normal and shearing stresses acting on different surfaces. And the question is whether these stresses are maximum values. If we were to rotate the element itself, there may be an angle itself where the normal and shearing stress becomes maximum. For instance, the tension here may not be maximum. We need to rotate it at some inclined angles before it will be maximum. As we rotate the element itself, there will be an angle where the normal stress on the surface is maximum. This angle of rotation is called theta p, which is also called the principal plane. Sigma max and sigma min are what we call the principal stresses. There are in general two principal planes which are 90 degrees apart, this and this. On the principal plane, there are no shearing stresses. The maximum principal stresses is also the most tensile one. In other words, if we have both faces that are in compression, the maximum principal stress is the one that is most tensile or the least compressive one. There's also an angle of rotation for the elements where shearing stress is maximum. This plane of maximum shearing stress is rotated by theta s and is also 45 degrees apart from the angle of principal plane. There are also two angles for the plane of maximum shearing stress and they are 90 degrees apart. There may or may not be normal stress when we have maximum shearing stress. To obtain the principal stresses and principal planes and maximum shearing stress, there are two methods. First is using equations and the other is using Mohr circle. For equations, we can use the equations here. Before using it, there are several conventions we need to stick to. First, sigma, which is the normal stress, is positive if tensile. Tau, shearing stress, is positive if the element's right-hand side is in the positive y direction. And theta is positive if it's rotated anti-clockwise. The element with positive convention is shown here. If the normal stress is compressive on the surface, we will set sigma to be negative in the equations. If shear stress on the right-hand side of the element points down, we will put a negative sign for the equations. If the signs are wrong, the results from the equations will be wrong, and this is very important that you stick to this convention when using equations. Theta p itself is your principal plane. There are in general two values of theta p, which is theta p plus 90 degrees. To get the principal stresses, we can use equation 7.14, which is sigma max and sigma min. For any other arbitrary rotation angle, we can use equation 7.5. And the principal plane can be solved using this equation. For maximum shearing stress, these are the equations. This is the angle of rotation to the plane with the maximum shearing stress. This is the equation for maximum shearing stress. And this is the associated normal stress when the element is experiencing maximum shear stress. If the element itself is rotated at any arbitrary angle theta, which may not be the principal plane or the maximum shearing stress angle, it may be just any angle, theta. As such, we can use these equations to solve for the corresponding sigma x, tau xy, and sigma y. The second method to find principal stresses and principal planes and maximum shearing stress is the Mohr circle. In fact, the equations you saw earlier can all be derived from the Mohr circle. For the Mohr circle, there are several conventions we need to stick to. First, if the normal stress on the surface is in tension, it will be on the positive x-axis of the Mohr circle. If the shearing stress on the surface turns the element clockwise, it will be on the positive y-axis. And the scale for x and y-axis must be the same. If they are different, then you will end up drawing a Mohr oval. The Mohr circle has x-axis as the normal stress and y-axis as the shear stress. We'll use this element to illustrate how to draw the Mohr circle. On this element itself, we have compression on the top and bottom and tension on the left and right. And we have the shear stress as illustrated here. This itself is the axis. On the x-axis, we have the normal stress, y-axis the shear stress. Let's look at this surface on the right. On this surface here, you will notice that we have a normal stress of 40, which is in tension, as well as a shear stress that's on 10, that's going upwards and rotating the element anti-clockwise. For normal stress is positive. For shear stress itself, because it rotates the element anti-clockwise, therefore it is negative shear stress. This itself will appear here, where sigma is 10 and tau is minus 10. On the other surface, we have a compression of 10 and a shear stress of 10. Compression is negative. Shear stress itself will rotate the element clockwise, as such shear stress is positive. The other point is here. The next step is to draw the Mohr circle, where we have a line that joins the 2 points, and subsequently we draw a circle where the radius of, or rather the diameter of the circle, is the line between the 2 points. This line itself corresponds to the element that is upright. To obtain the principal stresses and principal planes, we rotate the line such that it becomes horizontal. And the angle of rotation is 2 theta p. To get the principal plane, we'll just divide 2 theta p by 2, and then we get theta p, and we get theta p plus 90 degrees as well. Here, as the element is rotated anti-clockwise, theta p is positive. We can also get the value of sigma maximum and sigma minimum. We can use a ruler and protractor to measure. To obtain the maximum shearing stress, we rotate the line itself to become vertical. The angle of rotation is 2 theta s, and if we want to find the angle, it will just be theta s. And there will be two angles, theta s and theta s plus 90 degrees. Since this rotation is clockwise, theta s is negative. We can also obtain tau max over here. This is another example where we have compression on both sides. I'll leave it to you guys to solve it. This is the answer. Note that because the Mohr circle itself does not cut or encircle the origin, there will be both maximum in-plane and maximum out-of-plane shear stress. To get the maximum in-plane, it will just be the maximum value from the original Mohr circle. To get the maximum out-of-plane shear stress, we draw a larger circle that touches the origin. And the peak tau here on the new circle will be the maximum out-of-plane shear stress. As mentioned, if the Mohr circle touches or encircles the origin, there's only in-plane shear stress. If it doesn't, there will be out-of-plane shear stress, where we'll draw a larger circle and the maximum tau is the maximum out-of-plane shear stress. The value is also half sigma max or half sigma min. Now that we know the maximum, normal, and shearing stress, we will want to design the materials such that they are above these values. And there are several criteria for failure. For ductile materials, we have the maximum shearing stress criteria. For ductile materials as well, we have the maximum distortion energy criteria, which is the Vomisis criteria. For brittle materials, we have the ultimate normal stress criteria. If there is factor of safety, we will want to ensure that the factor of safety is accounted for appropriately. Apart from external forces causing stresses on elements, pressure vessels can also cause stresses. You can see pressure vessels as your can drinks, and when you shake it, the internal pressure will build up such that there's an outward force that causes stresses on the surface of your can ring. For a thin wall pressure vessel, where 2 times the inner radius over the thickness is greater than 10, we are able to find the circumferential stresses as well as the hoop stress using these two relationships. Note that R here is for the inner radius. There's also the principal shear strain, which is just using your principal stresses equation and substituting in these relationships. One more thing to note. When a question asks you to draw an element, and the stresses on the surface itself is compressive, you should draw the arrow pointing into the element as you can see over here, and put positive value for the sigma. You should not draw the arrow out and then you put a negative sign for sigma. This itself is the incorrect way of drawing stresses on the element. This is the correct way. Same thing for shear. If itself is an upward arrow on the right hand surface and tau is negative 10, you should draw the arrow downwards instead, and then you put tau as positive 10. We will now move on to the tutorial questions. In this question, we are given an element as shown, and we are told to find the principal planes and stresses. We will solve it using equations as well as Mohr circle. First, we will solve it using equations. For equations, these are the conventions we discussed earlier. On the x phase that you see over here, the normal stress is compressive. As such, sigma x is equals to negative 60. On the y phase itself, the normal stress is compressive. As such, sigma y is negative 40. For shear stress, the direction of the shear stress is upwards on the right side. As you can see over here at B, this means that my shear stress is positive. Using the equations for principal plane, tangent 2 theta p equals to this equation here, we can find that 2 theta p equals to negative 74.05 degrees. As such, your theta p will be negative 37 degrees and you plus 90 degrees to become 53 degrees. Do note that theta is positive if it's rotated anti-clockwise. For principal stresses, we can also make use of the equation here, and then we solve for it, and then we find that sigma max and sigma mean are equals to these values. Do note that sigma maximum is the one that is less negative. We are also asked to find out what is the orientation of the maximum in-plane shearing stress and the corresponding normal stress. We can do so by using the equations. This is the equation for the orientation, where we use tangent 2 theta s equals to the equation here, and we find that 2 theta s equals to 16 degrees. As such, theta s equals to 8 degrees, and you plus 90 degrees to become 98 degrees. Alternatively, we know that theta s and theta p are 45 degrees apart. As such, we can just add 45 degrees to theta p and arrive at the same answer. For the value of maximum shearing stress, we can also use the equations, and we get 36.4 megapascal. For the corresponding normal stress, we use the equations, which is sigma x plus sigma y over 2, and it's just negative 50 megapascal. We will now solve the problem using Mohr circle. These are the rules for Mohr circle. For the x phase of the element itself, the normal stress is compressive, and hence it will be on the left side of the y-axis, over here. The shear stress rotates the element anti-clockwise, and using this rule itself, the shear stress will be below the x-axis over here. It will be negative 35. As such, this is the point corresponding to your x phase. On the y phase, the normal stress is compressive, as such is negative 40. The shear stress rotates the element clockwise, as such shear stress is positive. Therefore, we have the second point over here. We then draw a line to link these 2 points, and then we draw a circle, which will become the Morse circle. To get the principal plane, we rotate the line from here to become horizontal. The angle of rotation is 2 theta p. We then obtain sigma max, sigma mean, as well as sigma average. For the principal planes itself, the angle of rotation is tangent to theta p over here is equals to this length divided by this length. This length is tau xy, and this length is sigma average minus sigma y. This is the same as the equation that we have solved earlier. Solving for it, we obtain 2 theta p equals to negative 74.05 degrees. Theta is hence negative 37 degrees, and then we add 90 degrees to become 53 degrees. Note here that because the rotation of the line itself to horizontal is in the clockwise direction, clockwise rotation is defined as negative. As such, the value here is negative. For principal stresses, we have sigma maximum equals to sigma average plus the radius of the circle. Sigma minimum is sigma average minus the radius of the circle. As such, we'll need to find out what radius is. Radius itself is given by this equation. You solve for it and you obtain 36.4 megapascal. And sigma average is literally just the average of sigma x and sigma y, which is just negative 50 megapascal. Substitute these two values into your sigma max and sigma min equation, and then you solve it and you obtain these two values. To obtain the orientation for maximum shearing stress using Morse circle, we'll rotate the line to become vertical, and the angle of rotation is 2 theta s. We also obtain tau max over here. To find theta s, we make use of this triangle. This is 2 theta s, as such tangent to theta s is equal to this length divided by this length. This length is sigma average minus sigma y, and this length is tau xy. And this is the same as the equations we have seen earlier. Solving, we obtain 15.95 degrees for 2 theta s, and theta s is 8 degrees, and 8 degrees plus 90 degrees to become 98 degrees. Note that the rotation here is anti-clockwise. As such, 2 theta s is positive. For the maximum value of shear stress, it is just the radius for the Morse circle, which is 36.4 megapascal. The corresponding normal stress itself is just over here, and is sigma average, which is just negative 50 megapascal. In this question, we have a steel pipe with an arm CDE. There are forces 3 kN upwards on C and 9 kN downwards at E. We are told to find principal stresses, principal planes, and maximum shearing stress at the point H. So what we do in step 1 is to cut at the cross section, where the element is over here, and then we define the axis. If the question gives you the axis, you must use back the same axis definition. If it does not give you the axis, you must define your own. In step 2, we transfer the external applied loads to the internal loads at the section. We look at the loads itself axis by axis. For the x-axis itself over here, we have 3 kilonewtons and 9 kilonewtons. When you combine them, it's downwards of 6 kilonewtons. That is at a distance of 150 mm away from the x-axis. This will cause a moments about the x-axis, that is 900 Newton meters. We use the right-hand rule to define the moments. For the y-axis itself, these 3 kilonewtons and 9 kilonewtons will resolve and get a 6 kilonewtons downward shear force acting over here. As such, there will be a shear force of 6 kilonewtons. For the z-axis, these two forces will create a torque about this axis. As such, this torque itself is given by 3 plus 9, which is 12 kilonewtons, times the moment up of 120 mm. And this is 1440 Newton meters. And we can use our right hand rule to define. In step 3, we transfer the internal loads to stresses on the element. We draw the element as such, which is the positive convention for the element. We have the z phase as well as the y phase. Now we look at the forces and moments on the x-axis and determine what kind of stresses it will cause on the element. On the x-axis itself, we have a bending moment. This moment itself is acting right at the center, and you can use the right hand rule to determine that the top part is undergoing tension and the bottom is undergoing compression. In between, along the neutral axis, there's no normal stress. As such, this moment does nothing to your element. On the y-axis, we have shear. For shear itself, there will be a shear stress, and shear stress is maximal along the center neutral axis. And since this element is at the center, this creates a shear stress over here. As the left-hand side surface of this element is going downwards for the shear stress, it is the same as what you have on the element as defined over here as downwards. As such, shear stress here, we'll put it as positive. For the z-axis, we have a torsion. Using the right-hand rule, it will cause the left face of the element to go down in terms of shear stress, which is the same as what we have in the element. As such, it's positive Tc over J. For sigma y and sigma z, it will just be 0. We will now resolve the stresses on the elements. And in fact, we only need to resolve for shear stress because normal stress are both 0. V here is 6000 newtons. Q here for hollow section is this. I for hollow section is this, which is second moment of area. T is the thickness of where we cut. The thickness itself is this plus this, which is 0.01 meters. T here is 1440 Newton meters as we obtained before. C is the outer radius because the element lies on the outer radius. J, polar moment of inertia for hollow section. Putting in all the known values for tau xy or tau yz, and we obtain tau yz equals to 55 megapascal. Now that the stresses on the elements are all obtained, we are ready to find out what is the principal stresses, principal plane, and maximum shearing stress at point H. We will first solve using equations. First of all, we need to define sigma y, sigma z, and tau yz using the conventions for equations, where this itself is the positive convention for elements. After using the convention, these itself are the values that you use for the equations. This is the equation for the principal stresses, sigma max, sigma min. We put in the values and we get sigma max is 55 and sigma min is negative 55. For the principal plane, we use the equation here 7.12, and this gives us 45 degrees and 135 degrees. For the maximum shearing stress, also the same, the equation, and we get 55 megapascals. We can also solve using the Mohr circle. This itself, we first draw the axis for sigma and for tau. For the element itself, on the z phase, we have sigma z is 0. As such, sigma z is 0, and tau itself is rotating the element anti-clockwise. As such, it will be below. So for the Z phase, the element will be here. For the Y phase here, the stress itself, normal stress is 0, and the shear stress will rotate the element clockwise. As such, it will be here. So we draw a straight line to join up the 2 points. And then we draw the Mohr circle. From here, it's easy to see that tau max, maximum shear stress, is just 55 megapascal. To get the principal stresses, we'll rotate this line to become horizontal. As we rotate it to become horizontal, we obtain sigma max and sigma min. And sigma max is just 55, and sigma min is just negative 55, because this is at the origin. For the angle of rotation, 2 theta p is just 90 degrees, as such theta p is 45 degrees and negative 45 degrees. Which means that we are able to rotate the line clockwise or anti-clockwise. In this question, we have a shaft AB that has a yield strength of 250 megapascal and a torque of 1500 Newton meters is being applied. We are asked to use the maximum shearing stress criteria to find the magnitude of P. The first observation we can make is that everywhere along the shaft, stresses are the same. We can hence define the element anywhere. So, we can cut anywhere, and then we define the axis and the element anywhere along the circumference, and we put the element here. We then transfer the external force and torque to the internal forces and torque. For this question itself, we can directly transfer this P and T over to the section at the cut. We then transfer the internal loads to stresses on the element. We first draw the element over here, which is based on the positive convention. We have the X phase and the Y phase. The first force P here will cause tension along the X direction, which is just P over A. Because it's in tension and the convention is positive for tension, therefore this is a positive P over A. The torsion itself will cause shear stress, and it will cause the right hand side of the element, the shear stress, to be upwards. According to convention, this is positive. As such, this is positive Tc over J. T here is given in the question 1500, C is the outer radius, J, the equation is given here. We substitute in the values and we obtain 89.68 megapascal for tau xy. Sigma y will be 0. We now define the maximum shearing stress criteria. The maximum shearing stress criteria says that tau max equals to sigma u divided by 2. Because sigma u is 250, therefore half of it is 125. For the element itself, tau max can also be obtained using the equations over here. We substitute equation 1 into equation 2, and then we solve, and we find that sigma x itself is equal to 174 megapascal. Given that sigma x equals to P over A, we can make P the subject, and then we find that P is equal to 264.8 kilonewtons. You can also solve the question using Mohr circle, which looks like this. I will leave it to you to work out. The next part of the question requires us to solve the same question using the maximum distortion energy criteria. The maximum distortion energy criteria is what we have seen in the notes. In this equation, we have sigma max, sigma min, as well as the sigma u. We also have the equations for sigma max given as such, which is sigma average plus radius, sigma minimum equals to sigma average minus radius. Because there's no stress in the vertical direction over here, therefore, sigma average is just sigma x divided by 2. Sigma x divided by 2 over here. We substitute equations 2 and 3 into equation 1 for sigma max and sigma min, and we obtain this form. After some manipulations, we obtain the equation over here. We then find the expression for radius r, which is just tau max, and is given by this equation. We substitute r into the equation over here, and then we solve further, and we obtain sigma x is equals to this expression. We substitute in the values for sigma u and then tau xy, and we obtain 195.9 megapascal. As P itself is equals to sigma x times area, P will be 297.9 kilonewtons. In this question, we have a compressed air tank with a certain pressure inside. In this case, there is both hoop stress and circumferential stress on the surface. We will need to determine the maximum normal stress and maximum in-plane shearing stress at the point A on top of the tank. In step 1, we'll cut at where the element is. This is the cut, and then we define the axis. We then transfer the external loadings to the internal loadings at this section. First, we look at the x-axis, which is along this axis. This external force, 5 kilonewtons, will create a torque about the x-axis. And using the right-hand rule, we can draw the arrows with double arrowhead as such. This torque is 5 kilonewtons times 500 mm, which gives us 2,500 Newton meters. About the y-axis at the cut itself, this external force will generate a moment about it, and this moment is 5 times 750 mm, which will give us 3750 Newton meters, and we use our right-hand rule to determine the direction of the double-headed arrow. For the z-axis, this 5 kilonewtons is along the same direction as the 5 kilonewtons. As such, there will be a shear of 5 kilonewtons over here. Remember, there is also stresses due to the pressure vessel. We then transfer the internal forces to stresses on the elements. The element itself is drawn here with positive convention, with x and y phase. This phase here itself is parallel to your circumference of the cut. This y phase here itself is parallel to your longitudinal axis. Along the x-axis itself, we have a torsion, and this torsion itself creates a shear stress on the element, such that the shear stress is along the circumference in the direction that is towards the right side. As such, it is in this direction, which is the same as the positive convention. Therefore, it's positive Tc over J. Along the y-axis itself, we have a bending moment. These bending moments will cause tension on top and compression below. As the element is furthest away from neutral axis, it will have maximum tension. As such, it will be given by my over I. For shear, maximum shear stress itself will be along the neutral axis. However, the element is at the top. As such, there will be no shear stress here. So for the z-axis, they will have no effect on the element. We also have the pressure cylinder, which will have tension forces along the x and y direction. In the longitudinal direction, we have PR over 2T. In the hoop of circumferential direction, we have PR over T. We can now solve the values of sigma y, sigma x, and tau xy using the equations that we have derived. For sigma y is PR over T, where P is the pressure given in the question, R inner radius of the compressed air tank, T the thickness of the skin of the compressed air tank. For tau xy as well as sigma x, these are the equations we obtained earlier. One thing to note C is outer radius and Y is also outer radius. With these values obtained, we are now ready to determine the maximum normal stress and maximum in-plane shearing stress. We can solve using equation or the Morse circle. Let us solve using equations. For sigma max is just sigma average plus radius, and this is the equation. We substitute in the values and then we obtain 45.1 megapascal. For tau max is just a radius and it's just 9.4 megapascal. We can also solve using Morse circle. This is the Morse circle that is drawn out for this question. I will not go through it and you can actually resolve it on your own. This comes to the end of tutorial 7.